Hello everyone and welcome. I'm excited to have you here today. We're about to dive into an interesting topic, coroutine syntax and structure. This is the first slide, so I just want to give you a quick overview of what's coming up. We'll explore how coroutines work, their syntax, and how to structure them effectively. So let's get started and make this a fun learning experience. All right, let's talk about the basic way to launch a coroutine. So you use the launch function inside a coroutine scope, like run blocking. This means that the coroutine runs concurrently with other code, and importantly, it doesn't block the main thread. In the example, we have a main function that starts with run blocking, which creates a blocking coroutine scope. Inside that scope, we launch another coroutine using launch. This inner coroutine performs a delay of 1 second, but notice that this delay is non-blocking. It allows other code to run while waiting. Right after launching that coroutine, we print hello. Because the delay is non-blocking, hello gets printed immediately and the world message appears after the delay. The key idea here is that launching coroutines this way enables concurrent execution without blocking your main thread, making your code more efficient and responsive. This approach ties into the overall theme of asynchronous programming, where we want tasks to run independently but still work together seamlessly. So let's talk about suspend functions. These are special functions in Kotlin that are marked with the suspend keyword. What makes them so powerful is that they can suspend their execution without blocking the thread they're running on. This means your app can stay responsive while waiting for long-running tasks. But there's an important point. Suspend functions can only be called from within coroutines or other suspending functions. This restriction helps manage concurrency in a safe and predictable way. For example, in the code snippet here, we have a suspend function called doWork. Inside it, we use, which pauses the function for 500 milliseconds, but crucially, it doesn't block the thread. Instead, it suspends only this coroutine, allowing other tasks to run smoothly. After the delay, it prints work done, to indicate the task is complete. This approach highlights how suspend functions enable efficient, non-blocking asynchronous programming, which is a core theme of our overall discussion today. They allow us to write code that's both readable and responsive, even when dealing with tasks that take some time to complete. All right, let's take a look at how returning results works in Kotlin coroutines. When you want to start a coroutine that will eventually give you a result, you use async. This creates a deferred result, which is like a promise that the value will be available later. To get that value, you call await on the deferred object. For example, in this slide, we start with val deferred async, delay 1000L plus result. This means the coroutine will wait for 1 second before returning the string result. Then, by calling println deferred await, we suspend the current coroutine until the result is ready and then print it out. This pattern is really powerful because it allows us to write asynchronous code that looks and behaves like synchronous code, making it easier to understand and maintain. It's a core concept in coroutine-based programming, helping us handle operations that take time, like network requests or long computations, without blocking the main thread. So remember, async starts the coroutine, and await is how we retrieve the result once it's available. Let's talk about coroutine context. When launching a coroutine, it's important to specify the dispatcher to control which thread it runs on. For example, you can use dispatchers, main for the main thread, dispatchers, I/O for input-output operations, or dispatchers, default for CPU-intensive tasks. By setting the dispatcher, you ensure that your code runs efficiently and correctly on the appropriate thread. For instance, if you write launch, dispatchers, I/O, that coroutine will run on the I/O thread pool, which is ideal for network or database operations. This way, you keep your UI responsive and avoid blocking the main thread. Understanding how to specify the dispatcher is key to managing threading effectively in your coroutines. It ties directly into the overall theme of controlling concurrency and optimizing performance in your app. Let's talk about structured concurrency. When working with suspend functions, it's best practice to use coroutine scope. This construct ensures that all the child coroutines launched inside it are completed before the scope itself finishes. It's important to note that coroutine scope waits for all its child coroutines to complete, but it does so without blocking the thread, which keeps our application responsive. For example, in the code snippet, we have a suspend function called doConcurrentWork. Inside it, we call coroutine scope and launch two separate tasks. These tasks run concurrently, but the function won't move forward until both are finished. This approach helps us manage multiple asynchronous operations cleanly and safely, aligning with the overall idea of structured concurrency, keeping our code predictable and easier to maintain. Let's talk about exception handling in coroutines. One of the key tools we have is the coroutine exception handler, which allows us to catch and respond to exceptions that occur within a coroutine. This is especially useful for managing errors gracefully without crashing the entire application. Another important concept is the use of supervisor jobs, or supervisor job, which helps us isolate failures in child coroutines. Unlike a regular job, where an exception in one child can cancel all others, a supervisor job ensures that if one child fails, it doesn't affect the rest of the coroutines running under that supervisor. For example, we can create a handler like this, where we define what happens when an exception occurs, such as printing an error message. Then, we include this handler in our coroutine scope along with a supervisor job. In our example, when we launch a coroutine that throws a runtime exception, the handler catches it, preventing the failure from affecting other coroutines. This approach is really powerful because it helps us build resilient, fault-tolerant applications by isolating failures and handling errors cleanly. It connects to our overall theme of managing asynchronous tasks effectively, ensuring our app remains responsive and stable even when some parts encounter problems. Let's talk about cancellation today. When working with coroutines, cooperative cancellation is key. You can use isactive or cancellation-aware suspend functions to handle this. Essentially, these tools let a coroutine check if it should stop running. And to actually cancel a coroutine, you call the cancel function. For example, imagine we have a job launched with launch. Inside, it repeats 1,000 times, printing a number each time. But if at any point isactive is false, the coroutine will return early, stopping the process. Finally, to ensure the coroutine completes its cancellation properly, we use cancel and join. This method cancels the job and waits for it to finish. This approach to cancellation is crucial because it keeps our applications responsive and prevents unnecessary work. It ties back to the overall theme of managing asynchronous tasks efficiently and safely. Now let's talk about channels, which are a fundamental part of coroutine communication. Think of channels as a kind of pipeline that allows coroutines to send and receive data efficiently. This setup follows the producer-consumer pattern, where one coroutine produces data and another consumes it. In the example, we create a channel and launch a coroutine that sends squared numbers into it. Notice how we loop through numbers 1 to 5, sending each squared value into the channel. Once all values are sent, we close the channel to indicate that no more data will come through. On the receiving end, we can iterate over the channel directly, which automatically waits for new data until the channel is closed. This makes asynchronous communication smooth and straightforward. Channels are essential because they help us coordinate work between coroutines without resorting to complex locking mechanisms. They keep our code clean and make concurrent programming more manageable. Remember, using channels effectively ties into our overall goal of writing efficient, non-blocking, asynchronous applications. Let's take a closer look at Flow. Flow is a powerful tool for working with asynchronous reactive streams, and it allows us to apply various operators like map, filter, and collect to process data efficiently. For example, in this simple flow function, we emit numbers from 1 to 3 with a slight delay between each emission. Then, we filter out even numbers, keeping only the odd ones, and map those remaining numbers by multiplying them by 2. Finally, we collect and print the results. This demonstrates how flow enables us to build a reactive pipeline that processes data step by step in a clear and concise manner. Overall, using flow helps us handle asynchronous data streams smoothly, making our code more readable and reactive, which ties back to our theme of modern, efficient programming.